Let us now try to model a simple reaction taking place in the plug flow reactor. In the past, we have looked at examples of reactions taking place in a CSTR. CSTR is a vessel with a stirrer in which the concentration or temperature inside the reactor is homogenized because of the ideal action of the stirrer. In a plug flow reactor, that's simply not true. What you have in a plug flow reactor is reaction happening in a tube where we assume that the velocity profile is flat. That means the fluid elements at all points, right? Whether it is in the center of the tube or in near the walls of the tube, all travel at the same velocity. So this is a flat velocity profile. So anywhere from the center of the tube to the walls of the tube, the velocity is the same, and we can call that velocity as v. This is an idealization over what we usually see in flow through tubes, where the velocity profile is supposed to be parabolic type, right? So you have velocity profile like this. That means at the center, if you call center as 0 in the radial direction, at the center, the velocity is the maximum. And as you move in the radial direction towards the tube walls, the velocity gets smaller and smaller, and exactly at the wall, the velocity is assumed to be 0. This is something called the no slip condition, etc. So this is the parabolic velocity profile. This is not what we are looking at. We are looking at this kind of an idealization. And what happens here is the concentration of, let's say, the reactant is high at the entry point into the reactor. And as you proceed through the reactor, what happens is the concentration of the reactant falls. The concentration of the product, let's say product species, is 0 and the reactor entrance, and it builds up, right? As you go inside the reactor, the product concentration increases. I'm just showing you some kind of typical cartoon kind of figures. But I hope you understand that within the reactor, the concentration of A or the temperature will not remain the same throughout the reactor. From the entrance of the reactor to the exit, there is typically a concentration profile or a temperature profile. The conditions inside are not homogeneous, right? As you go from the reactor entrance to the reactor exit, the conditions are not homogeneous. So this is a big difference between the CSTR and the plug flow reactor. For certain reactions, people prefer the plug flow reactor. For other kinds of reactions, they prefer the CSTR. There are lots of considerations, and when you do a course on chemical reaction engineering, you would come across these kind of conditions under which one configuration is better than the other configuration, etc. Now, presently returning to this modeling of this plug flow reactor, what we are going to assume is the feed consists of pure R. So the species is called R. We assume isothermal reaction, that means there are no heat effects, so we do not have to bother about the energy balance. It is enough for our purposes to consider only the mass balance. And we assume that the reaction is of first order. The reaction is R going to S. So R is the reactant species, S is the product species. So the rate of reaction minus R for species R is given to be K times CR. And the CR, the concentration of species R, will vary as we go into the reactor. At the entrance of the reactor, we can expect the concentration of R to be maximum. And as you go towards the exit of the reactor, at the exit of the reactor, the concentration of species R will be the lowest. I'm taking into account the nature of this reaction, R going to S. The concentration of species R is going to decrease as we walk from the reactor entrance towards the reactor exit. Of course, things can still change with time, right? Because if the feed flow rate or the feed concentration fluctuates, then of course this will travel into the reactor, and at any point in the reactor, what will happen is things will change with respect to time. So time can still be a factor, but certainly things are going to change with respect to position as well. We also assume, for simplicity purposes, we assume that the density is constant. There are no density variations from the reactor entrance to the reactor exit. That simplifies writing of mass balances, right? To a certain extent, for sure. Now, we also assume that the velocity is constant throughout. So, in the plug flow condition, we say that the velocity profile is flat, and that is maintained throughout the reactor. There is no acceleration or deceleration of the fluid elements inside the reactor. So they travel as a flat profile and they just keep going like that, right? So there is no change in the velocity v. So these are some of the assumptions we make in order to make the modeling simple. Now, A is the cross-sectional area of the reactor. So that's, in the pipe, if you look through it, the circular cross-section, we can expect that to have a cross-sectional area A. So A is the symbol that represents the cross-sectional area. So it is going to be pi times r squared, where r is the radius of this tube. We can also say A is going to be pi d squared by 4, where d is the diameter of the tube, and so on. So feed enters at z is equal to 0. So this axial position is labeled as z. So z is equal to 0 means we are talking about the reactor entrance. Z is equal to L means we are talking about the reactor exit. So this reactor is of length L in meters. All right, so these are some of the assumptions about the chemistry of the reaction taking place inside this reactor, the symbols related to the configuration of the reactor, etc. So what we are going to do is we are going to look at a control volume. That means we are going to take a look at the reactor section between value z is equal to z and z is equal to z plus delta z. So we are going to focus our attention on this elemental volume of width delta z. So we are just going to focus our attention there, and because we can take delta z to be as small as possible, we can assume that the conditions are homogeneous for this small delta z zone. So it'll come through in our discussions later. So this is where we are going to focus on, and as usual, what we will do is we are going to focus on this control volume of thickness delta Z. That means of volume A delta Z. A is the cross-sectional area. So that if you multiply by the length of the control volume, you're going to get this A delta Z. So this space has got this volume A delta Z. A is the cross-sectional area. You multiply it with delta Z. So that will be like the volume of this section that we are going to focus on. And we are going to focus on it over the time period, time t to time t plus delta t. So again, our focus is on the system, specifically this control volume of size A delta Z from t is equal to t is equal to t plus delta t. Now these are some of the variables and the units that we will adopt. The velocity of the stream is going to be denoted by the symbol v, and the units are meters per minute. The cross-sectional area of the tube is indicated by the symbol A, as you have seen. Its unit is meter squared. The rate of reaction should be minus RR, exactly, right? So we are talking about species R. So the rate of reaction is the rate of disappearance of R, that is given to be moles of R per meter cube per minute. Exactly the same, because we are assuming first order reaction. Kindly note that this should actually be minus RR. And here it should be rate of disappearance of R, because R is the reactant species here. And then the units should be moles of R per meter cube minute, right, in the denominator. So this is the usual units we use for the rate of reaction. And because it is a first order reaction, the reaction rate constant is going to be minute inverse. So these are the usual units that we have seen before. For this control volume of size A delta Z, we are doing the usual stuff. Over this time interval delta T, how many moles of R has come to be accumulated within this control volume? That is given by the moles of R in the control volume. So CV is the control volume. So moles of R in the control volume at time t plus delta T minus the moles of R in the control volume at time t. If you take the difference, you're going to get the moles of R accumulated in the control volume during this time interval that we are observing the system. And why does this accumulation happen? Possibly it is because moles of R has entered the control volume during this time interval delta t. So it has entered this control volume at position Z. And some R has left the control volume during this time interval delta t at position Z plus delta Z. Remember? So if you take a look at this control volume, so the feed enters here, right? For this control volume, here is where things enter, right? So it is at Z. Where it leaves the control volume is at Z plus delta Z. So that is why I'm saying moles of R entering the control volume during time interval delta t happens at position Z. And where the moles of R leave the control volume during the same time interval, that occurs at position Z plus delta Z. And what has happened within this control volume is, because of the reaction, some amount of R has disappeared. That is this particular term. So for R, because it is a reactant species, you have accumulation, you have the inflow, you have the outflow, and you have the consumption or disappearance of R. So very similar to what we did for other reacting systems that we have considered before, except that we are now looking at this control volume A delta Z. That's the volume that we are focusing on. A delta Z is the volume. A subtle point is that in this volume, the material enters at location Z and material leaves at location Z plus delta Z. That's about the subtle point that we need to know. Now, once we have understood and we are in agreement with this equation, then we can now turn towards symbols. So this is the phenomena, and now we get into the engineer's job of putting symbols, because that is the language we speak, right? We speak in terms of symbols and the subsequent models that we will get. So let's go to that step further. This is exactly like what we wrote before, right? So it's like VCR. What is V? V is the volume in meter cube. CR is moles of R per meter cube. So if you multiply the two, you will get moles of R. Because it's a mass balance, we are going to write it in moles of R. So instead of V, right, what is V here in our case? We are focusing on that control volume of size or volume A times delta Z. So instead of V that we use for CSTR, we are going to replace V by A delta Z, because that is the fluid element we are focusing on. Concentration of R at time t plus delta t. Just recall, previously we used to write for CSTR, if the same thing was happening in CSTR, we would have written VCR at t plus delta t minus VCR at time t. This would give us the accumulation of R over the time interval delta t. We are doing the same thing here, except that we are saying, because we are focusing on that control volume, which has a volume of A delta Z, we are going to replace volume of the reactor by volume of the element that we are looking at. Essentially, what we have is, we have A delta Z CR at t plus delta t. So this is going to be in moles of R, minus A delta Z CR at time t. Right? Again, it is going to be moles of R at time t. The difference should be equal to inflow minus outflow minus reaction. In the case of CSTR, we would have written QCR, right? QCR delta T, where Q is the volumetric flow rate, CR is the concentration, and delta T is the time. Kindly look at the previous examples. Here, instead of Q, Q is volumetric flow rate in meter cube per minute. We are going to replace Q by velocity times cross-sectional area. Velocity is in meters per minute. Cross-sectional area is in meters squared. So if you multiply V and A, we get the volumetric flow rate Q. So instead of Q, which we wrote for CSTR, we are just going to write it here as V times CA. So Q times CR times delta T, exactly like what we wrote before, except for two improvisations. One is, we are going to say Q is equal to V times A. The second thing is the entrance. This is the amount of A entering. If you multiply all these things, you will get moles of R. So moles of R enters this control volume at location Z, as we saw before. So we say at Z. The outflow is going to be similar symbols, except that we say the outflow occurs at location z plus delta z, as we have argued before. Fine. So we have taken care of the inflow and the outflow terms. Now coming to the reaction term, for a CSTR, we would have written this term as KCR V delta T, because the rate of the reaction KCR is written in moles of R per meter cube per minute. That's always the rate of the reaction. Always the rate of the reaction as units of moles of species divided by volume times minute, right? So that is what it is. And then V is in meter cube, delta T is in minutes, let's say. So minutes cancels with minutes, meter cube cancels with meter cube, leaving us with moles of R, which is dimensionally consistent with the other terms. Now, here, as we have done before, instead of V, we will just say A delta Z, because our volume that we are now focusing on is this control volume with volume equal to A delta Z. So instead of V, as we did for the other terms, we said A delta Z. I'll remove the ink from the slide so you can have a clear look at the terms of the equation. Now we do the usual trick. We divide throughout by A delta Z delta T. So if you divide the left hand side by A delta Z delta T, what will happen is A delta Z will cancel out, leaving you with CR, the concentration of species R at time t plus delta T, minus the concentration of R at time t divided by delta T. So that's what you see here. Equals, now if you come to this term, when you divide this by A delta Z delta T, A cancels out, delta T cancels out, leaving you with VCR at Z divided by delta Z. VCR at Z divided by delta Z. And when you divide this term by A delta Z delta T, again A cancels with A, delta T cancels with delta T, leaving us with minus VCR at Z plus delta Z divided by delta Z. So I hope you understand the origin of this term in this equation, just by dividing this term by A delta Z delta T, we would get that. And the last term, when you divide it by A delta Z delta T, what happens is this cancels out, leaving us with minus KCR. So at this point in time, after we have divided everything by A delta Z delta T, we are left with this. So now the next usual trick is take the limit when both delta Z and delta T tend to 0. That means you're looking at very small reactor thickness. So delta T is infinitesimally small. We're also looking at delta T being almost 0. That means we are observing the system for a very, very short time duration. So that's when we can invoke calculus and say this term will reduce to dou CR by dou T, right? Because it is CR at T plus delta T minus CR at T divided by delta T. So that is like dCR by dt. But here we recognize the fact that CR depends both on time and position. Therefore, instead of saying dCR by dt, we will use the partial derivative because CR is going to depend on both t and z. So I cannot write dCR by dt, rather I'll write dou CR by dou t, right? So this becomes this when delta t goes to 0. What happens to this as delta t goes to 0? Please understand that it is flipped. It is VCR at z minus VCR at z plus delta z divided by delta z, and delta z is tending to 0 now. So the order is flipped. Please note in this term it is t plus delta t minus at what happens at t. Therefore, you get dou CR by dou T. But here, it is not what happens at Z plus delta Z minus what happens at Z. It is what happens at Z minus what happens at Z plus delta Z. Therefore, you will get a negative sign because the order is flipped. And when delta Z goes to 0, what you see is you will get dou by dou Z of VCR. So I hope you understand the meaning of this negative sign or the origin of this negative sign, simply because the fluid element in our notation, right? When we call the left side as the reactor entrance and the right side as the reactor exit, and we start looking at Z from the entrance towards the exit, right? So the fluid element enters at Z and leaves at Z plus delta Z. So what happens is you get term in this particular way, which is the opposite. So you can always take this and say, I can write this as minus VCR at Z plus delta Z minus VCR at Z divided by delta Z. So I've taken the minus out. So this is exactly the same as this. And as delta Z goes to 0, we understand this is nothing but uh, d by dz of VCR. And this minus sign is there. We can put the minus sign here. That's how you get this. All right. So again, we use the partial derivative because CR is going to be a function of both T and Z. So we have to use the partial derivative. And KCR with a negative sign stays as it is. Right? Nothing happens to KCR as delta Z goes to 0 or delta T goes to 0. So what you have here is this particular equation, dou CR by dou T equals minus V dou CR by dou Z minus K times CR. And CR is a function of both T and Z. Or you can write it as CR is a function of Z and T, doesn't matter. So what we get here is a partial differential equation, not an ordinary differential equation. We are going to get a partial differential equation because there are two independent variables here, which are time T and position Z. The dependent variable is CR. There are two system parameters here if you want to look at it that way. One is the reaction rate constant and the other is the flow velocity. So you could change K and see how the system responds, or you could change V and see how the system responds, or work with other kinds of what we would call as dimensionless quantities like Beckley number and stuff like that. All right. So this is characteristic of the distributed parameter system where things change with both position and time. So I hope you are able to understand the features of this example. Now coming to a tubular reactor, it's not a plug flow reactor now, it's a tubular reactor. We will not look at it in detail, but everything else is the same, right? Except now I'm calling the reactant to be A, the product to be B, and the reactant is pure A, entering at x is equal to 0, and reaction takes place inside this tubular reactor. And what happens is the product and the unreacted A exit at x is equal to L. So this is just a different relabeling, but the key difference is that it is a tubular reactor. It's not a plug flow reactor. In which case, the dispersion effects may be interesting, right? In plug flow, we do not assume dispersion in the velocity front. But here, what happens is we are going to have dispersion, which is characterized by this term D, the diffusivity coefficient, if you like. So this is related to Fick's law, which you probably have learned already or will learn soon, right? It's called Fick's law of diffusion. So the term has origins from there. So if that phenomena is important, then you have to bring that in. And that phenomena is important typically when you have tubular reactors as opposed to plug flow reactors. So when you have plug flow, D is equal to 0 and this term drops off. And this is what we got in the previous example, right? But when D is not 0, right? When the dispersion is significant, as it can be in a tubular reactor, then this term cannot be ignored, right? So we have to have this term. what happens is the system still remains a partial differential equation system, where because the concentration C of species A changes with both time t and position x. Still, it is an unsteady state system because things can change with respect to time. And interestingly, when you assume steady state, let's say dou C by dou t will become zero because things don't change with respect to time at steady state. Then you will get this expression, right? So this is going to be zero at steady state. Therefore, you will get this expression. Exactly what we have here equated to zero because this becomes zero. The interesting thing is there we do not write dou, right? We just write the regular derivative d because now C at steady state is not going to be a function of time. It's just going to be a function of position. So you will get this. So at steady state, a partial differential equation becomes a ordinary differential equation because C is going to be a function of only x when you have steady state. And this would be called a second order ordinary differential equation because the highest derivative is the second derivative. So to conclude, based on the few examples that we have seen here, modeling involves writing down dynamic mass and energy balances, making some valid assumptions, and we can always reduce the dynamic models to steady state models by setting the time derivative equal to zero. In general, what happens is modeling using first principles, conservation of mass, energy, momentum, etc. Though we have not looked at momentum balance here, but whenever you invoke first principles and write models for lump parameter systems like the CSTR, you will get ordinary differential equations like CSTR or just the mixer, etc. You will get ordinary differential equations. And when we have distributed parameter systems like the one that we looked at, plug flow reactor or tubular reactor, we are going to get partial differential equations for distributed parameter systems. Of course, at steady state, the partial differential equations may become ordinary differential equations. And usually we will have nonlinear models because the kinetics can be nonlinear like a second order reaction. And oftentimes what we see is the product of manipulated variable Q and a disturbance variable CAF, right? We have seen this kind of product terms appearing in many of our models. Therefore, when you multiply one variable with another variable, you will have some bilinearity at least, right? So nonlinear models are frequently common. And therefore, numerical methods are needed. We cannot solve nonlinear models analytically, as we have stated a few times. So this concludes our presentation, and we will catch up in a different video later. Thank you.